Hello everybody and welcome to this Matlab tutorial. I'm wearing my Matlab hat, that means we're doing some serious coding today. I hope you're ready. My name is Felix, I'm a PhD student here in the Auditory Cognition group at Newcastle University, and today I'm going to show you how to work with and visualize spiking data. Okay, I'm sure you've all seen plots like this where you have the raw trial-wise spiking response plotted on top of an average time trace or plotted in addition to a histogram. Today I'm going to show you how to produce this kind of figure. The script I'm going to show you assumes that you have already extracted your trial-wise event-aligned spike times. Your spike times can be aligned to the onset of the trial, to stimulus onset, or to any behavioral event. The data I'm working with is cortical multi-unit activity that I've recorded in the auditory cortex in response to the presentation of the same sinusoidal tone. Okay, so let's dive right in. I've created a figure window here on the left hand side and I'm gonna add some axes to this figure window. We're gonna start plotting our raster plot first, and the variable that contains all of my data is called SP times, short for spike times. As you can see, it's a cell array that contains 45 cells. That means we've presented our tones 45 times, and each of those cells contains the timings of the threshold crossing. That means the spike times. So what we need to do is we need to loop through all of those trials, starting from trial 1, looping all the way up to trial 45. So let's do that for our first trial. For the sake of clarity, we're going to assign the spike times of this trial to the variable spikes. As you can see, we've detected 75 spikes in this trial, and the numbers here correspond to the timings of those action potentials in relation to the onset of the sound. What we're doing next is we're going to replicate this vector 3 times, and we are assigning the output to the variable x spikes. So x spikes is now an array that contains 75 columns for our 75 spikes. Oh, be gone. And then it contains 3 rows. In addition to that, we're gonna create a variable y spikes that has the exact same dimensions, but that is entirely filled with NaN, short for not a number. Okay, so why are we doing this? We want to code efficiently. That means we don't want to plot each individual spike separately. So what we're trying to do here is to plot a single line object for each trial that contains all the spikes that we've detected. So critically now, we need to replace the first row of y spikes with a number that is I trial minus 1, and the second row of y spikes with a number that is I trial. And those numbers determine the offset of our line object in the plot. So we're going to start at 0 and we're going to move up to 1. And this now allows us to plot x spikes against y spikes. And whoa, we have plotted the spiking response of our first trial. So time 0 here corresponds to the onset of the sound. Our tones were 200 milliseconds long, and each of the black lines here corresponds to an action potential. Now, if we look at our second trial, then you'll see that the numbers in y spikes have actually moved up by a factor of 1. So the first row is now filled up with 1s, the second row is filled up with 2s, and the third row is still filled with NaNs. And since this determines the y offset of the line object, we'll see that we get another line object plotted right on top of our first trial. So let's do that for all of our trials. And voila, we've produced a nice looking raster plot. So again, time 0 corresponds to the onset of the sound. Stimulus duration was 200 milliseconds. Each of the black dots here corresponds to a single action potential, and each of the rows corresponds to a single trial. You see that we are getting nice sound-evoked activity. Okay, so we care about our plots, which is why we want them to look nice. Thus, we're gonna adjust the X and Y limits. We're only gonna show 2 tick labels, and of course we're gonna label our axes. Whoa! That is a nice looking raster plot. Okay, we have created an excellent raster plot, and now it's time to somehow summarize the neuronal activity that we're seeing here. So this is the raw spiking activity in response to each tone presentation, and we now want to kind of get an idea of what this neuron is doing on average. And we're gonna look at a peristimulus time histogram, or PSTH, first. What we need to do in order to create a plot like this is we need to loop again through all of our trials from trial 1 to trial 45, and we're gonna concatenate all spike times in one variable. So we initialize a variable called all here. We then loop through all of our trials, extracting the spike times, and then we kind of concatenate those spike times to this variable. So all now contains every single spike time that we've ever recorded, and it contains 2215 spikes. Okay, so let's add another axis, and when you plot a histogram you need to decide on a number of bins, which basically gives you the temporal resolution. I decided to go for 100 bins, which defines the bin size to 5 milliseconds, because the entire presentation period we are plotting here is 500 milliseconds long. So if we divide that up in 100 bins, we get a bin window of 5 milliseconds. Okay, and then we just need to plot it with the histogram command. Please. We haven't defined our bins. Alright. So there we go. This is our histogram, and I don't like this color, which is why I'm changing this to black. Okay, the y-axis now shows us the number of spikes in each bin, and just by showing you this, of course, changes when I change the bin size, right? If I go for larger bins, you get more spikes per bins. If I go for smaller bins, you get less spikes per bin. But we're gonna stick with 100. Then again, we're gonna adjust our X and Y limits. We only show 2 tick labels, and of course we label our axis. And the number of spikes per bins doesn't necessarily tell us a lot about the rate of this neuron, the firing rate of this neuron. So we need to convert the number of spikes per bin into frequency. And in order to do that, we need to convert our Y tick labels. So as I've mentioned before, this entire duration here is 500 milliseconds long. And we now need to calculate our bin duration, which I've told you before is the length of this entire period divided by the number of bins, which gives us 5 milliseconds. And we then need to figure out how many bins actually fit into 1 second. So we take 1000 milliseconds divided by the bin duration and find out that we actually can fit 200 bins into 1 second. Great. So next, we need to get our Y tick labels. We need to convert them into frequency. So let's try that with 100. So we're gonna pick this label over here. We're gonna divide it by the number of trials we're having. This gives us the average spikes, the average number of spikes per bin, and we're gonna multiply that by the number of bins in 1 second. So 100 spikes per bins, So 100 spikes per bin translates to 444.444 Hertz. And we're doing this for all of our y-tick labels. Store them in the variable new label, and we're assigning this variable to our axis. And then of course, this here is no longer spikes per bin, but it's now measured in firing rate, which is measured in Hertz. Great, so we now have created a PSTH that kind of gives us an idea what the raw spiking activity does on average. And we are seeing nice stimulus evoked activity over here in response to the presentation of a pure tone. Up to this point, we have visualized the raw trial-wise spiking response in this raster plot, and we have evaluated the average spiking activity, the average neuronal firing rate in this PSTH over here. And wow, look at this stimulus evoked activity. Isn't that beautiful? What we're doing next is we're gonna go one step further and show a spike density function. A spike density function is closely related to the PSTH, but instead of working with the raw spike times, you fit to each individual spike a Gaussian curve. And this gives you an idea of the probability of a spike at each point in time. So let's dive right in and define our resolution for this spike density function, which is 1 milliseconds. We're defining the width of the Gaussian curve that we are fitting to each spike, which is 5 milliseconds in this case, and we are creating a time vector that is 500 entries long, and that is necessary for the creation of the spike density function. The process of creating a spike density function entails fitting a Gaussian curve to each of the individual spikes. So we need to yet again loop through all of our trials from 1 to 45. We are assigning the individual spike times to the variable spikes. As you can see, in the first trial we again have 75 spike times, and we're then looping through all of the 75 spikes in this trial. As mentioned, we're gonna center the Gaussian at the time of the threshold crossing, and we're gonna assign this to the variable mu. So for the first spike, this will be at minus 0.1921, which will be somewhere about 200 milliseconds before the onset of the sound. We then calculate the actual Gaussian curve, which I've just for easier readability split into two parts over here, and we're assigning the output to the variable Gauss. And we can plot this, and what you'll see is a nice sharp Gaussian curve with a 5 millisecond standard deviation. We're going to do that for all of our spikes now. So let's do that. Okay, and let's again look at this variable. And what you see is where about in time those spikes were detected. So for each spike, we're getting a vector that shows us the Gaussian curve, and that is 0 at any other point. Okay, so this plot is showing you the average spike density function for our first trial. It already resembles closely the PSTH we are seeing here. You can also see the same or similar pattern in the raster plot, and we're doing a similar procedure now for each of our 45 trials. Let's do that. Add another axis to our figure window. Of course, we have other figure windows open. So let's add another axis to our figure window, and let's visualize the spike density functions for each of the individual trials. So here on the y-axis shows you the number of trials, and this again is time And you can see that across trial there is some variability involved in neuronal responses, which is to be expected, but overall the pattern is similar across trials, and you get a huge ramp up in neuronal activity after the sound onset. Let's make this plot look nice and also change the color map. And we are now not really interested in a trial-wise description of the spike density function. We have the raw spiking data shown over here in the raster plot, so this is really not necessary. What we are interested in is the average spike density function, which looks like this. And as you can see, this closely resembles the PSTH and also gives you an estimation of the firing rate at each individual point in time, but critically, the spike density function is an estimation of spike probability, whereas the PSTH is really based on raw spiking data. Okay, so there you have it. This is how to work with and how to visualize spiking data. Today I have shown you how to create a raster plot which gives you a visualization of the raw spiking response on a trial-by-trial basis. I've also shown you how to produce PSTHs, which estimates the average neuronal firing rate based on the raw data. And I've also introduced you to the concept of spike density functions, which give you an estimation of the probability of a spike at each point in time. If you liked that video, if you want to learn more details about this kind of analysis, or if you want to dive deeper into the analysis of neuronal data in general, leave me a comment, I'll get back to you. Thank you so much for watching this video, I very much appreciate it. I'll see you in the next video, bye bye.